Axons come in two forms, covered and uncovered. Axons come in two forms, covered and uncovered. There is covered axon and there is uncovered axon. Don't worry about anything else right now. Just covered and uncovered. Some axon is covered, some axon is uncovered. That is very important for signal transmission in the majority of our nervous systems. A covered axon is going to be similar to a wire that's covered. Like I'm looking at this projector right here and I see like the wire on the projector, there's a cable and the cables are covered. So it's like that kind of covering. It's an insulative layer. It's covered by something. Then some parts of the axon are uncovered. But there are axons in the peripheral nervous system that are completely uncovered. They're uncovered by, wait guys, oh God, I like the students to work for me. What do you call the glial cell in the peripheral nervous system that covers axons? No, I didn't say the myelin sheath. What do you call the cell? Schwann cell, yeah, the Schwann cell, right? And what do you call it in the central nervous system? Uh-oh, the oligodendrocytes. Very good. You didn't say it 10 times at home. Remember last week? I told you say it 10 times at home every day for 10 days. And you're like, what? And I can say oligodendrocyte. So can you. Oligodendrocyte, oligodendrocyte, oligodendrocyte. Yeah, that's a hard word. So you have to say that a few times. You can write it 10 times too. You can do that. But that's the way you kind of do it, to memorize it, because that's a really hard word. So, you see, the reason I say covered and uncovered, because students all know what the myelin sheath is, but they don't get that it covers and there's uncovered sections too. So, covered means those parts of the axon that are covered by a myelin sheath. In the central nervous system, it's the oligodendrocytes that do the covering. In the peripheral nervous system, it is the Schwann cells that do the covering. You're all with me? Okay. In the peripheral nervous system, it is the the Schwann cells that do the covering, and in the central nervous system is the oligodendrocytes that do the covering. The oligodendrocytes and the Schwann cells are both types of glial cells.
When you say in peripheral is Schwann cells, and then in the central nervous system is what's the other one?
Oligodendrocytes.
That's in the central nervous system.
Yep. Okay, so covered. When I say covered, I just mean covered by axon that's covered by a myelin sheath created by one of those two cells, depending on where it is. It'll be on the slide. Yeah. So here is an unmyelinated. So myelin is here, M-Y-E-L-I-N. M-Y-E-L-I-N. So myelin. There are certain neurons in the nervous system that are not covered by myelin. These are called unmyelinated, right? It's right there on the slide. Unmyelinated axon. Not every neuron is myelinated, which is why I don't teach it that way. Now, see, on unmyelinated axon, what happens is it's only action potential that moves the signal forward. So an unmyelinated axon, it's only action potential that's going to move the signal forward. Right here, you see it? So here's like the idea that the signal's moving forward. Here would be the signal at this point. Here's just like a little example. It's only action potential that moves that signal forward. Now here's the problem. It's very slow. When you compare myelinated axon to unmyelinated axon moves that signal forward at a much slower rate than myelinated axon. When you have the myelinated axon, it's much more efficient. The kind of conduction that happens along an unmyelinated axon is called continuous conduction. The type of conduction that happens along an unmyelinated axon is called continuous conduction. It continues once, and this is the other feature of action potential. Once an action potential starts, it doesn't stop until it reaches its logical conclusion. Once an action potential starts, it doesn't stop until it does what it's supposed to do. Until it reaches that terminal, it doesn't stop. So it moves forward. It moves forward more slowly than electrotonic potential, and it doesn't stop. You can't stop it, okay? So it doesn't move backwards. That's important to know. Electrotonic potential kind of spreads a bit, just like fast and dirty. But action potential moves forward in one direction, doesn't move backwards. We'll learn why in a minute. And it also is going to reach its end.
You said that the type of conduction across the myelinated axon is called continuous.
Continuous conduction. It continues. It goes on and 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 on. There's no breaking it up. So continuous conduction is not broken up by electrotonic conduction or electrotonic potential. It's just action potential continuing till its logical end. A continuous conduction is just action potential continuing till its logical end. Are you with me there? Good. So, that's continuous conduction. The other type of conduction is called saltatory conduction. Now, saltar, S-A-L-T-A-T-O-R-Y, or as my high school Spanish teacher said, saltar. Saltar. See? No. I think my high school Spanish teacher's Spanish is very good. Okay. And continuous conduction, as you can see here, is much slower than saltatory conduction. But why don't we like to say saltatory? Why don't we like to say jumping? Dangerous. Jumping's dangerous as hell. Don't let them do it. Keep the kids away from the jumping yard. The jumping yard. No, jumping's not dangerous. But in this logical game, it's like a mixed metaphor. Jumping is dangerous because I always got confused when I was learning this. Is like, like when I was learning this stuff by these kind of pictures. Like, here's like arrows going this way, arrows going this way. It's jumping. There's like there's arrow here. There's arrow. It always, I didn't understand that. And a lot of different textbooks have that. And if you look at another video on YouTube or look at other resources, you might see a lot of arrows going in all directions. It's going in one direction. Okay? Don't worry about all those arrows. They're just follow my lecture and hopefully we all get it. So you see the difference here at 10 milliseconds or microseconds? Do you see the difference here between how far this signal has gotten with continuous conduction versus with saltatory conduction? Do you see that? So at the beginning, they're kind of at the same place. Now here at 5 microseconds, it's or milliseconds. I'm not sure what that is. It's at this point. They're about the same point. But then at 10, this is really far behind, and that one's all the way up ahead. Do you see that? Okay. So that means that continuous conduction is much slower than saltatory conduction. It also means that in order for signals to be effectively transmitted, you need to have a combination of electrotonic potential and action potential together. It's only the combination that helps the two to transmit the signal effectively. We're going to be looking now how the two, electrotonic potential and action potential, work together in order to affect signal transmission.